Imagine a major financial institution in 2026 still relying on T+1 batch processing. A sophisticated fraud ring initiates a coordinated attack at 2 a.m. Your system, scheduled to run at 6 a.m., remains blissfully unaware as millions are drained in minutes. By the time the Spark batch job finishes its transformation and loads the data into the warehouse, the trail has gone cold. This is the reality of the batch-first mindset treats data as a historical artifact rather than a living asset. In the high-frequency world of 2026, the latency between an event occurring and its availability for analysis isn't just a metric, it's a liability. We are seeing the total collapse of the traditional wait and process model because business windows have shrunk to milliseconds. But what exactly is the structural flaw that makes batch processing so dangerous in a modern ecosystem? Teaser, the answer lies in how we fundamentally define freshness, which we will dismantle right now. To survive the demands of 2026, we must pivot from being reactive observers to proactive architects. The real-time Lakehouse blueprint isn't just about faster hardware, it's a fundamental architectural shift. We are moving away from the rigid silos of the past, where streaming was an add-on and batch was the truth. In this new paradigm, every piece of data is treated as a stream from birth. By leveraging open table formats like Apache Iceberg, we can achieve ACI transactions on top of object storage, allowing us to merge the speed of stream processing with the reliability and scale of a data lake. This allows for continuous intelligence, where the distinction between hot and cold data becomes a fluid tiering strategy rather than a physical barrier. Understanding this shift is the first step toward building a resilient platform. Question: but is this just a theoretical ideal, or are the market forces truly mandating this change? Let's look at the evolutionary trajectory of data architecture over the last 2 decades to understand why 2026 is a tipping point. We started with the monolithic data warehouse, optimized for structured SQL, but failing at scale. Then came the data lake era, which solved the scale problem but created data swamps lacking governance. By 2024, the Lakehouse emerged to bridge this gap. However, as we approach 2026, we are entering the era of the Agentic Lakehouse. Here, AI agents and autonomous systems require sub-second access to the most recent data to make real-time inferences. The architecture must now support unified metadata, schema evolution, and instantaneous consistency across distributed regions. This isn't just evolution, it's a survival requirement for the next generation of data-driven enterprises. Payoff: while the history is clear, the current market statistics reveal a much more urgent pressure for architects today. Industry data indicates that by 2026, over 60% of all new data pipelines will require real-time or near real-time capabilities to remain competitive. This 60% rule signifies that real-time is no longer an edge case for specialized niches like high-frequency trading. It is the baseline for retail, logistics, and healthcare. As a data platform architect or a technical professional, your role is transitioning from a system maintainer to a value stream orchestrator. You must design systems that can handle the sheer volume of 2026's data sphere while ensuring cost efficiency through intelligent hot and cold tiering. We are moving toward a store once, access everywhere philosophy. If you fail to implement a storage layer that supports this concurrency and speed, your entire platform becomes a bottleneck. Bridge: to solve this, we need a universal foundation, which is why in the next chapter, we will dive deep into Apache Iceberg as the ultimate universal storage layer for 2026. In the data architecture landscape of 2026, the format war has reached a definitive conclusion. Apache Iceberg has emerged as the universal abstraction layer that decouples storage from the compute engine. Unlike traditional Hive-style partitioning, which relies on directory structures, Iceberg treats a collection of files as a single logical table. This is achieved through a robust, metadata-driven approach that provides a consistent view of the data regardless of the underlying object storage. From an information management professional engineer's perspective, this standardization is the cornerstone of data governance and interoperability. It allows organizations to move away from proprietary silos and toward an open standard architecture, where data is no longer held hostage by specific vendor tools. But what exactly happens under the hood when we commit a transaction to this layer? Question: to understand the reliability of Iceberg, we must look at how it manages state through its complex metadata hierarchy. Iceberg's magic lies in its metadata tree. When a write occurs, Iceberg doesn't just add a file, it creates a new snapshot. This snapshot points to a manifest list, which in turn points to manifest files that track individual data files. This hierarchy enables ACID transaction-specifically snapshot isolation, ensuring that readers always see a consistent state of the data, even while writes are in progress. For high concurrency environments in 2026, this eliminates the dreaded partial read errors that plagued early data lakes. Furthermore, this structure allows for time travel, enabling users to query the table as it existed at any specific point in history by simply referencing an older snapshot ID. Teaser: while this sounds perfect for reliability, you might wonder how it compares to other heavyweight weights like Delta Lake or Apache Hudi in terms of performance and ecosystem reach. By 2026, the comparison between Iceberg, Delta Lake, and Hudi has shifted. Delta Lake remains strong in the Spark ecosystem, and Hudi excels in incremental upserts for specialized streaming. However, Iceberg has won the broad ecosystem battle because of its neutral governance and the widespread adoption of the Iceberg REST catalog. Major cloud providers and independent engine vendors have converged on Iceberg as the default lingua franca. Unlike Delta, which was historically tied to a single vendor's optimization path, Iceberg was designed from the ground up to be engine agnostic. This makes it the ideal choice for a multi-engine strategy where Flink handles the stream, Spark handles the heavy batch, and Trino serves the interactive ad hoc queries. PayOFF, the real operational advantage isn't just engine support. It's how Iceberg handles the evolution of data over time without breaking downstream systems. Two hidden features make Iceberg indispensable for 2026 architectures: hidden partitioning and full schema evolution. Traditional Hive partitioning required users to manually manage partition columns, often leading to query errors if the partition logic changed. Iceberg handles this internally. You can change your partitioning strategy from daily to hourly without rewriting a single byte of data. Similarly, schema evolution in Iceberg is a metadata-only operation. You can add, drop, rename, or reorder columns with zero impact on existing data files. This flexibility is critical for modern agile data teams who need to adapt to changing business requirements without expensive data migrations. Question: if the storage is this flexible, how do we build a unified engine strategy around it to maximize efficiency? In the 2026 data platform, the write once, query everywhere philosophy is finally a reality thanks to Iceberg. Imagine a pipeline where Apache Flink writes real-time streaming data into an Iceberg table, while simultaneously, Trino performs sub-second analytical queries on that same table, and Apache Spark runs heavy machine learning workloads once a week. Because all these engines share the same Iceberg catalog, they all see the same consistent ACD-compliant view of the data. This eliminates the need for complex data movement between specialized databases. We are moving toward an engine-agnostic architecture where the best tool for the specific task is used without the overhead of data silos or ETL pipelines for synchronization. Teaser: this architectural freedom brings a massive shift in how we think about data ownership and vendor lock-in. From the perspective of an information management PE, data sovereignty is a primary concern. Relying on a single vendor's internal storage format is a massive strategic risk. Apache Iceberg mitigates this by providing an open standard that ensures your data remains yours. If you decide to switch your primary query engine from vendor A to vendor B in 2026, you don't need to migrate your petabytes of data. You simply point the new engine to the existing Iceberg catalog. This level of portability is essential for meeting modern regulatory requirements and ensuring long-term data durability. Open standards aren't just a technical preference. They are a risk management strategy for the modern enterprise. Question: but does an open standard mean zero maintenance? Absolutely not. Maintaining an Iceberg-based Lakehouse requires proactive management. Since Iceberg creates a new snapshot for every commit, over time, the metadata and small data files can accumulate, leading to performance degradation. This is where compaction and snapshot expiration become critical. You must regularly schedule maintenance tasks to merge small files into larger, more efficient Parquet files and delete orphan files that are no longer referenced by any snapshot. In 2026, many of these tasks are automated via catalog-level optimization services, but an architect must still understand the underlying mechanics to tune the platform for cost and performance. Payoff: ignoring these maintenance tasks will turn your high-performance lakehouse into a slow, expensive data swamp. To wrap up Chapter 2, Apache Iceberg provides the universal storage layer that simplifies our enterprise architecture by standardizing how data is stored, evolved, and queried. By decoupling storage from compute, it enables a multi-engine strategy that is robust, flexible, and future-proof for the challenges of 2026. We've seen how its metadata-driven approach solves ACD and schema evolution issues, but storage is only half of the story. In a world moving toward real-time, how do we handle the massive influx of data while balancing performance and cost? Teaser: in the next chapter, we will bridge the gap between the storage layer and real-time processing by exploring hot and cold tiering mechanics. In the 2026 data landscape, the concept of a batch window has effectively vanished. To build a resilient lakehouse, we must treat the message bus not just as a buffer, but as the central nervous system of the enterprise. Whether you are using Apache Kafka or the more modern Redpanda, this layer decouples high-velocity producers from the storage-heavy lakehouse. In a professional architecture, we look for write-path stability. By utilizing the Kafka protocol, we ensure that every transactional event is captured with microsecond latency before it is ever committed to an Iceberg table. This decoupling is what prevents a spike in user traffic from toppling your analytical engines. However, simply capturing data is only half the battle. The real magic happens when we begin to reason about this data while it is still in flight. But how exactly do we perform complex operations on data that never stops moving? Teaser: the answer lies in a new breed of SQL engines that we will examine in the next scene. Modern data platforms in 2026 have shifted from store then process to process as it flows. Engines like Rising Wave or Flink SQL allow us to define materialized views directly on the stream. Imagine joining a real-time click stream with a dimension table stored in Iceberg. In the past, this required complex Spark jobs. Today, we use streaming SQL to handle window joins and aggregations in memory. This incremental processing model ensures that by the time data hits the lakehouse, it is already cleaned, enriched, and ready for consumption. This reduces the compute load on your warehouse significantly because you aren't reprocessing the same historical data over and over. This is the hot part of our tiering strategy where freshness is measured in milliseconds. But wait, what if the data is trapped in an old-school relational database? Question, does that mean we have to go back to slow daily batch jobs for our SQL Server or Oracle data? To bridge the gap between operational databases and the lakehouse, we rely on log-based change data capture, or CDC. Using tools like Debezium, we can tail the transaction logs of databases like PostgreSQL or MySQL without placing any significant load on the production system. Unlike traditional ETL, which queries the database every hour and risks missing intermediate changes, CDC captures every insert, update, and delete as an event. This allows the lakehouse to maintain a near-perfect replica of the operational state in real time. This is essential for event-driven architectures, where the analytical side needs to react instantly to business changes. From an information management PE perspective, CDC provides the audit trail and consistency that legacy batch pipelines simply cannot offer. But even with the best tools, things go wrong. Payoff in the next scene, they'll show you why your perfect pipeline will fail when network lags or schemas change. Reliability is the most overlooked aspect of real-time design. In the real world, data arrives late, networks flap, and schemas evolve without notice. We must architect for back pressure, ensuring that if the Iceberg commit process slows down, our streaming engine doesn't crash, but instead slows down the ingestion rate. Furthermore, we must address the exactly once delivery challenge. Apache Iceberg's transactional nature is a lifesaver here. It allows the streaming engine to checkpoint its progress so that if a failure occurs, we can resume without duplicating data. We also need a dead letter queue for records that don't match the expected schema, preventing a single malformed packet from stopping the entire pipeline. Mastering these edge cases is what separates a prototype from a 2026 production-ready platform. Now that we have captured the data reliably, we must decide where it lives. Teaser, let's dive into the economics of storage tiering to see how we save millions in cloud costs. Storage tiering is no longer an optional optimization. It is a survival requirement for the data-intensive enterprise. In our 2026 architecture, we classify data into 3 distinct tiers based on its value density. The hot tier resides in high-performance NVMe storage or specialized S3 Express one-zone buckets, holding the most recent 24 hours of data for sub-second dashboards. The warm tier is where Apache Iceberg truly shines, managing Parquet files on standard object storage for the last 30 to 90 days. Finally, the cold tier moves aged data into deep archive storage like Glacier, where it is still searchable but at a significantly lower cost. As an architect, your goal is to maximize the performance-to-cost ratio. If you store everything in the hot tier, you'll go bankrupt. If you store everything in the cold tier, your analysts will quit. Question, but how do we move data between these tiers without manually writing move scripts every night? Automation of data movement is handled by Iceberg's table maintenance and lifecycle management. In 2026, we utilize Object Lambda and Iceberg's REST catalog to trigger data migration based on age or access patterns. For example, once a data file in the hot tier reaches 100 MB or is 1 hour old, a compaction job merges it into the warm tier as a large Parquet file. This process, known as compaction, is vital because it solves the small file problem that plagues real-time ingestion. By rewriting small JSON-like chunks into optimized, columnar Parquet files, we improve query performance by up to 10x. We also automate the snapshot expiration to clean up old versions, ensuring we don't pay for ghost data. This lifecycle isn't just about saving money. It's about maintaining a lean lakehouse. Payoff, but if the data is spread across different tiers, how does a user query it without knowing exactly where it is? The holy grail of data architecture is the unified query interface. From the analyst's perspective, they should only see a single table, say, fact sales, regardless of whether the data is 5 seconds old or 5 years old. This is achieved through query federation and table virtualization. Engines like Trino or Starox can intelligently split a single SQL query. The hot portion goes to a streaming database or fast NVMe store, while the historical portion goes to the Iceberg tables on S3. The engine then joins these results before returning them to the user. This abstraction layer is what allows the underlying hardware to change without breaking a single BI dashboard. It creates a seamless experience where data is always accessible, regardless of its physical tier. Question, however, does this level of abstraction lead to cost surprise when an analyst queries 5 years of cold data by accident? Concluding our look at real-time mechanics, the information management PE views hot and cold tiering as a governance and control framework. It's about total cost of ownership and environmental sustainability. By 2026, the energy footprint of your data platform will be as important as its latency. By aggressively tiering data to cold storage, we reduce both financial costs and carbon footprints. We must establish guardrails, for example, setting row-level policies that prevent expensive full-table scans on the cold tier unless authorized. We've built a real-time, cost-optimized lakehouse that is ready for human analysts. But next wave isn't human. Teaser, in the next chapter, we look at architecting for the agentic enterprise, where AI agents become the primary consumers of our real-time lakehouse. In the landscape of 2026, we are moving beyond simple chatbots to agentic AI autonomous systems that don't just answer questions but execute complex workflows. For these agents to be effective, the real-time lakehouse must evolve into a central control plane. Traditional RAG systems often suffer from data staleness, where the LM makes decisions based on hour-old data. By utilizing Apache Iceberg's snapshot isolation and incremental reading capabilities, we can feed fresh, high-velocity data directly into vector databases or AI memory layers. This ensures that the agent's context window reflects the absolute current state of the business, from inventory levels to market fluctuations. The Iceberg table format acts as the source of truth, providing a unified interface where structured transactional data and unstructured vector embeddings coexist. However, as the number of agents grows, a new challenge arises. How do we prevent these autonomous entities from accessing sensitive information they shouldn't see? This leads us directly to the critical issue of centralized governance in a decentralized AI world. But wait, if everyone including AI is hitting the lakehouse at once, how do we keep the metadata from collapsing under the pressure? In an agentic enterprise, data governance is no longer just about compliance. It is a fundamental security requirement for AI safety. We need a unified governance layer, a control plane that spans across streaming ingestion and static storage. This is where modern catalog services come into play, providing a single point of entry for security policies. By managing permissions at the Iceberg metadata level, we can enforce role-based access control, RBAC, that remains consistent whether the data is being accessed by a Flink streaming job, a Trino SQL query, or an autonomous AI agent. This one security policy approach eliminates the silos between hot streaming data and cold historical data. We must ensure that the credentials used by AI agents are tightly scoped and audible through the Lakehouse transaction logs. This architecture prevents privilege escalation within AI workflows and ensures that every data point has a clear lineage. But as we centralize the governance, we must be careful not to create a centralized bottleneck that slows down innovation. This leads us to the concept of the data mesh. Is it possible to have both centralized control and decentralized ownership in a real-time environment? The ultimate goal for the 2026 enterprise is to align the real-time lakehouse with data mesh principles. In this paradigm, data is treated as a product, and ownership is shifted from a central IT team to individual business domains like sales, logistics, or finance. Each domain manages its own Iceberg tables, which act as standardized data products that other domains and their AI agents can consume in real time. This decentralization is enabled by the one storage, multiple engines philosophy of Iceberg. A logistics domain might use Flink to update their inventory tables every few seconds, while the finance domain uses Starox to run sub-second analytics on that same data for real-time scoring. This architecture allows for enterprise-scale scalability because it removes the single point of failure inherent in monolithic data warehouses. We are effectively building a distributed brain for the company, where every department contributes to a shared, real-time knowledge base. But theory is one thing. How do these concepts perform under the pressure of real-world financial markets or global retail chains? Let's transition from architecture to the front lines of industry adoption. Let's examine a top-tier financial firm that successfully migrated from a complex Lambda architecture to a unified Iceberg-based real-time lakehouse. Historically, they maintained two separate pipelines, a batch track for historical reporting and a streaming track for real-time fraud detection. This caused massive data silos and logic drift, where the two systems often produced conflicting results. In 2024, they began consolidating these into a single Iceberg stream processing architecture. By 2025, they reached a state where every transaction is ingested via Flink directly into Iceberg tables, supporting both sub-second fraud scoring and long-term regulatory reporting simultaneously. This migration reduced their infrastructure costs by 40% and improved data consistency to 100%. The timeline shows a clear progression from fragmented data to unified intelligence. It's a powerful lesson in how simplifying the stack leads to higher reliability. However, while finance focuses on precision, the world of retail faces a different demon: global supply chain lag. How did a global retailer handle millions of SKU updates across thousands of stores in real time? In the retail sector, real-time visibility is the difference between a sale and a missed opportunity. A global retail giant implemented a real-time lakehouse to optimize their entire supply chain, reducing data lag from hours to mere seconds. The process starts at the point of sale POS and warehouse sensors, where events are streamed into a lakehouse using Apache Iceberg's merge-on-read strategy to handle high-frequency updates without blocking readers. This allows their inventory management system to see exactly what is on the shelf at any given moment across 5,000 locations. By utilizing Iceberg's time travel feature, they can also perform instant what-if analysis, comparing current inventory levels to historical patterns during flash sales. The result was a 15% reduction in overstock and a significant increase in customer satisfaction. This end-to-end process demonstrates that the technical choice of table format directly impacts the bottom-line business metrics. But be warned, achieving this level of performance isn't just about picking the right tools. Many companies fail during the implementation phase. What are the common anti-patterns that could sink your 2026 project? As we close this chapter, we must look at the hard-earned lessons from the field. Success in 2026 requires avoiding the common pitfalls of Lakehouse implementation. First, over-engineering is a silent killer. Don't build a complex real-time system for data that only needs to be updated daily. Second, ignoring metadata size can lead to performance degradation as your Iceberg snapshots grow. So does the manifest file size, requiring regular compaction and cleanup. Third, the engine mismatch using a heavy batch engine for sub-second queries will lead to excessive latency and costs. You must choose your compute engine based on the specific latency tier of your data. Finally, never forget the governance gap. Implementing technical layers without clear ownership policies is a recipe for a data swamp. These mistakes are why many architectures break. But now that you know what to avoid, how do you make the final choice? In the next and final chapter, we will reveal the P selection matrix, the ultimate blueprint for selecting the right engines and tiers for your specific enterprise needs. Are you ready to build the architecture that survives 2026? When selecting your data lakehouse stack for 2026, the primary debate remains self-managed versus managed services. From an information management professional's perspective, this is a critical trade-off between total cost of ownership and operational agility. For large-scale enterprises requiring extreme customization and fine-grained control over Iceberg's REST catalog or custom storage layouts, a self-managed approach using Kubernetes and open-source Iceberg components like Tabular or Project Nessie is often preferred. However, for organizations prioritizing time to market, managed services like Snowflake or Databricks offer seamless integration at the cost of higher per-unit processing fees. We must evaluate these based on 4 pillars: scalability, compliance, interoperability, and cost predictability. The choice you make today will define your platform's rigidity for the next 5 years. But cost isn't just about the license, it's about the performance architecture you choose for your specific latency needs. How do these choices impact your bottom line when data volume hits the petabyte scale? Data architecture is essentially the art of balancing latency requirements against financial constraints. In a 2026 environment, we categorize patterns into 3 distinct tiers. The pure streaming pattern, utilizing Apache Flink with Iceberg, provides sub-second latency for use cases like real-time fraud detection, but it requires significant state management overhead and higher compute costs. On the other end, micro-batching through Spark provides cost-efficient high throughput at the expense of minute-level latency, ideal for daily executive reporting. The unified approach, often referred to as the Kappa architecture, seeks to simplify this by treating all data as a stream, yet it demands rigorous hot and cold tiering to remain sustainable. Architects must plot their specific use cases to determine the optimal landing zone. However, even the most optimized stack will fail if it's built on a proprietary foundation that blocks future evolution. Is your current architecture flexible enough to handle a 10x increase in stream velocity without a total rewrite? As we look beyond the 2026 hype cycle, the most resilient architectures are those built on open standards rather than transient vendor features. The open Lakehouse paradigm, centered around Apache Iceberg, serves as a universal interface that decouples storage from compute. This allows you to swap engines moving from Trino to Starox or Spark to Flink without rewriting your entire data catalog or reformatting your storage layer. As an architect, your role is to ensure that metadata remains a first-class citizen, preventing data swamps through automated compaction and snapshot management. Remember the principle: data outlives its processing engine. By investing in the Iceberg standard today, you are essentially buying an insurance policy against the unpredictable technological shifts of the late 2020s. Now that we have the blueprint, let's synthesize everything we've learned into a final executive summary. But wait, what are the absolute non-negotiables you must implement before the year ends? As we conclude this lecture series, let's revisit the critical pillars of a 2026-ready Lakehouse. First, real-time ingestion is no longer optional. It is the baseline for the agentic enterprise where AI agents require fresh context. Second, Apache Iceberg has moved from being a feature to becoming the standard for table formats, enabling true multi-engine interoperability. Third, the separation of hot and cold data tiers using object storage and sophisticated metadata management is the only way to scale without breaking the bank. Finally, automated data governance and quality checks must be integrated directly into the streaming pipeline, not added as an afterthought. These 5 elements form the foundation of a modern data platform that can survive the transition from batch-heavy legacy systems to real-time, AI-driven environments. But before you begin implementation, you need a final sanity check of your current system. Are you ready to see the ultimate checklist that separates the visionaries from the legacy-bound? The journey to a real-time Lakehouse is a marathon, not a sprint. This final checklist serves as your strategic roadmap. You must verify if your Iceberg maintenance, tasks like orphan file removal and manifest compaction are fully automated to prevent performance degradation over time. Check your streaming state management. Are you prepared for multi-region failovers? Does your schema evolution policy support the rapid changes required by LLM-driven applications? As professional architects, our goal is to build systems that are not just functional, but sustainable and evolvable. The 2026 landscape will favor those who prioritized open standards and real-time agility over short-term convenience. I hope this blueprint provides the clarity needed to lead your organization's data transformation. This concludes our deep dive into the 2026 Lakehouse. Thank you for joining this masterclass, and I look forward to seeing your architectural breakthroughs in the field. This was the final chapter, but your implementation journey starts today.